August 22, 1943. School of Tank Technology, Chobham, England. Dr. Robert Stevenson examines a failed transmission gear from a captured Tiger I tank. The gear is massive, 8 inches in diameter, 2 inches thick, hardened steel designed to transfer 700 horsepower from the Maybach engine to the drive sprockets. The gear tooth is sheared completely off, not cracked, not worn, sheared, a clean fracture through hardened steel that should be nearly indestructible. This is not the first failed Tiger transmission Stevenson has examined. It is the 7th. Every captured Tiger tank delivered to Chobham arrives with transmission damage. Some minor, some catastrophic. This one is catastrophic. The entire final drive assembly destroyed. Metal fragments throughout the gearbox. The transmission failed so violently that it locked the drive sprockets. The tank stopped moving, became a stationary pillbox. Eventually was abandoned by its crew and captured intact by British forces near Tunis in May 1943. Intelligence reports indicate that Tiger transmission failures are common, extremely common. More Tigers are lost to mechanical breakdown than to enemy fire. The statistics are remarkable and almost unbelievable. Of approximately 1,300 Tigers produced by August 1943, fewer than 700 are operational. The rest are broken down, awaiting repair, awaiting parts. Or abandoned because repair is impossible. The Tiger tank was supposed to be Germany's answer to Soviet heavy armor. Invincible, unstoppable, armed with the legendary 80 Kinoumiya gun. Armored with 100mm frontal plate, powered by a 700 horsepower engine, capable of destroying any Allied tank at ranges exceeding 2 kilometers. On paper, the Tiger is the most formidable tank in the world. In practice, the Tiger cannot reach the battlefield. 50% of Tigers suffer major mechanical failure before completing their first operational mission. Most of these failures are transmission-related. Stevenson is a metallurgist. Before the war, he worked for Vickers Armstrong analyzing steel for naval construction. When war started, the War Office recruited him to analyze enemy armor and weapons. He has examined captured German tanks since 1941, has seen Panzer IIIs, Panzer IVs, captured intact or destroyed. The German tanks are generally well engineered, reliable. The transmissions function adequately, not the Tiger. The Tiger transmission is a disaster. German designers created a tank that the German transmission industry could not adequately support. The result is a weapon system that fails mechanically before it can engage the enemy. Stevenson's job is understanding why. He begins with the failed gear, examines the fracture surface under magnification. The fracture is brittle. No plastic deformation, no ductile tearing, just a clean break through the material. This indicates the steel failed suddenly under stress, without warning, without gradual degradation. One moment the gear was transmitting torque, the next moment it shattered. Stevenson measures the gear's hardness using a Rockwell tester, presses a diamond indenter into the gear surface, measures how deep it penetrates. The hardness reading is 62 HRC, Rockwell C scale, extremely hard. Harder than the specification for transmission gears. Transmission gears should be around 58-60 HRC, hard enough to resist wear, soft enough to resist brittle fracture. This gear is too hard. Stevenson tests multiple locations on the gear. Surface hardness is consistently 62 to 64 HRC. He cuts the gear in half, tests the core hardness. The interior measures 52 HRC. The surface is much harder than the core. This indicates case hardening. A heat treatment process where the surface is hardened while the core remains softer and tougher. Case hardening is normal for gears, provides wear resistance on the surface, maintains toughness in the core, but the case depth and hardness must be controlled precisely. Too much surface hardness creates brittleness. The gear will shatter under shock loads. This Tiger gear has excessive surface hardness. The case is too hard and too deep, 4 millimeters deep. Normal case depth for gears this size should be 2 to 3 millimeters. The excessive case depth and hardness make the gear brittle, prone to fracture under heavy loads. Stevenson needs to understand the microstructure. He cuts samples from the gear, polishes them to mirror finish, etches them with nitric acid to reveal the grain structure, examines them under a metallurgical microscope at 500x magnification. The microstructure shows martensite. A very hard, brittle phase of steel, formed by rapid cooling from high temperature. Martensite is desirable in controlled amounts, provides hardness, but excessive martensite without adequate tempering creates brittleness. Stevenson sees almost pure martensite in the case. Very little tempered martensite, very little retained austenite. The steel was hardened but not adequately tempered afterward. Tempering is a heat treatment that reduces brittleness. The hardened steel is reheated to moderate temperature. This allows some of the martensite to transform into tempered martensite. Softer, tougher, less brittle. Proper tempering is essential for gears, provides the balance of hardness and toughness needed to survive shock loads. This gear shows inadequate tempering. The martensite is untempered, brittle, ready to fracture. Stevenson examines 6 more failed Tiger gears. All show the same pattern: excessive surface hardness, deep case depth. Untempered martensite, brittle fracture. The problem is not isolated to one gear or one transmission. It is systemic. Every Tiger transmission uses gears with inadequate heat treatment. The gears are too hard and too brittle. They will fail under the stress of normal operation, especially under the extreme stress of combat maneuvering. Sharp turns, sudden acceleration, abrupt stops. These maneuvers create shock loads on transmission gears, loads that exceed normal operating stress. Properly treated gears can absorb these shocks. The Tiger gears cannot. They shatter. Stevenson writes a preliminary report dated August 28, 1943. The report documents the metallurgical analysis, describes the excessive hardness, explains the inadequate tempering, estimates the operational impact. The conclusions are significant and damning. If you are watching this video right now, you are part of a very specific audience. You are not here for simplified history. You are here for the actual engineering, the real metallurgy, the chemistry and physics that determined who won and who lost. This channel exists for people exactly like you. Subscribe now. Click the button below. Every week we publish videos revealing technical failures and triumphs that decided battles. The kind of deep analysis you will not find anywhere else. Do not just watch. Subscribe. Join the community of engineers and analysts who want the truth about how equipment performed and why. Click subscribe now. The report continues. Analysis of transmission gears from captured Tiger Y tanks reveals severe metallurgical deficiencies. Surface hardness exceeds specification by 10–15%. Case depth exceeds specification by 30–50%. Microstructure indicates inadequate tempering following carburization. The resulting material exhibits brittle fracture characteristics. Estimated operational effect. Transmission gears will fail under shock loads encountered during combat maneuvering. Failure mode is catastrophic. Sudden fracture with no prior warning. Once fracture initiates, the transmission becomes inoperable. The tank is immobilized. Recommend dissemination to Allied armor commanders. German Tiger tanks are vulnerable to mechanical failure. Aggressive maneuvering by Allied tanks may induce Tiger transmission failure, even without direct combat. The report goes to Major General Percy Hobart, commander of the British 79th Armoured Division. Hobart is an innovative thinker, understands that destroying enemy tanks is not only about firepower, it is also about exploiting weaknesses. If Tiger transmissions fail under stress, then Allied tactics should create stress, force the Tigers to maneuver, to turn sharply, to accelerate and decelerate. Each maneuver increases the probability of mechanical failure. Hobart circulates Stevenson's report to armor commanders. Classified secret. Limited distribution. The report includes tactical recommendations. When engaging Tiger tanks, attempt to force aggressive maneuvering, flanking attacks, rapid position changes. Create situations requiring the Tiger to turn sharply or reverse direction. These maneuvers stress the transmission, may induce mechanical failure. A Tiger with failed transmission is a Tiger removed from the battle without expending ammunition. The recommendations reach field commanders in September 1943. Some are skeptical. The idea that you can defeat a tank by making it drive seems absurd. Tanks are designed to move. Transmissions should withstand maneuvering, but the skeptics try it anyway. During engagements in Italy in October 1943, British tank commanders report unusual observations. Tigers that maneuver aggressively sometimes stop moving. Not destroyed, not burning, just stopped. Crews abandon them. Later examination shows transmission failure. The pattern repeats. Sicily, Italy, Normandy. Tigers break down during combat at rates far exceeding normal mechanical failure rates. German after-action reports describe the problem. Mention transmissions failing during engagement. Attribute it to combat stress, to poor maintenance, to inadequate spare parts. Do not realize the root cause is metallurgical, that the heat treatment process is fundamentally flawed, that every Tiger transmission is a mechanical time bomb waiting for sufficient stress to trigger catastrophic failure. Stevenson continues analyzing captured Tigers through 1944, examines transmissions from tanks built in different months, different factories. The pattern is consistent. All show excessive hardness. All show inadequate tempering. The problem is not one factory or one production batch. It is endemic to Tiger production. The question is why? Why would Germany build transmissions with inadequate heat treatment? Germany has excellent metallurgists, excellent heat treatment facilities. The knowledge exists. The capability exists. Why are the gears wrong? Stevenson investigates German heat treatment procedures. Reviews captured technical documents. Interviews captured German engineers. The answer emerges slowly. Germany is under intense production pressure. Tigers are needed desperately on the Eastern Front. Production schedules are compressed. Every Tiger must be completed as quickly as possible. Heat treatment is a bottleneck. Carburizing gears takes hours. Heating them in a carbon-rich atmosphere to infuse carbon into the surface, then quenching in oil to harden, then tempering to reduce brittleness. Each step requires time, requires furnace capacity, requires skilled workers. Germany is running out of all three. Time is inadequate. Furnace capacity is inadequate. Skilled workers are being conscripted into military service, replaced by forced laborers and minimally trained personnel. The replacement workers do not understand metallurgy, do not understand the importance of precise temperature control, do not understand that tempering is essential. They follow simplified procedures. Carburize, quench, ship. Tempering is skipped or abbreviated, saves hours per gear, increases throughput, allows more Tigers to be completed per month. The cost is reliability. The gears are hard but brittle, will fail under stress. But the failures happen later, in the field, not in the factory, not during acceptance testing. The factory meets its production quota, delivers Tigers on schedule. The transmission failures are someone else's problem. This is a pattern that repeats throughout late-war German production. Quality sacrificed for quantity. Procedures simplified. Corners cut. The equipment looks fine, performs fine under light conditions, fails catastrophically under combat stress. The Tiger transmission is one example. There are dozens of others. Stevenson documents this in his reports, notes that the problem is systemic, not specific to one component or one system. Germany's industrial base is collapsing. Quality control is evaporating. The equipment being produced is inadequate, even when new, will only get worse as it ages and wears. This analysis proves correct. By 1944, German equipment reliability is catastrophic across all systems: tanks, aircraft, submarines, trucks, artillery. Everything is breaking down at rates that would be unacceptable in peacetime. In wartime, when the equipment is desperately needed, the breakdowns are crippling. Germany cannot sustain military operations, not because of lack of courage or tactical skill, because the equipment does not work, because transmissions fail, because engines seize, because steel is inadequate, because metallurgy is wrong. Pause here if you have made it this far. You are not a casual viewer. You are someone who wants to understand engineering at a level most people never consider. This channel is built for you, for people who care about heat treatment procedures, about Rockwell hardness values, about tempering temperatures and microstructure. Subscribe now and activate notifications. We publish 2 videos per week. Each one dives deep into technical details that decided battles. The next video reveals another catastrophic German engineering failure. You do not want to miss it. Click subscribe. Click the bell. Be part of a community that values technical depth over superficial storytelling. Subscribe now. After the war, Allied technical intelligence teams systematically examine German production facilities, document the processes, interview the workers. The story of Tiger transmission manufacturing emerges in detail. The gears were produced by multiple subcontractors. ZF Friedrichshafen was primary, also Maybach, also smaller firms. Each facility used slightly different procedures, but all faced the same pressures. Produce more, produce faster. Quality is secondary. The workers described the environment: 12-hour shifts, minimal breaks, constant pressure from supervisors, production quotas that must be met regardless of circumstances. The heat treatment furnaces run continuously, loaded with gears, heated, quenched, unloaded, immediately reloaded. No time for proper temperature verification, no time for adequate tempering cycles. The process that should take 16 hours is compressed to 8. The gears come out hard, but wrong. One worker, a Czech forced laborer named Josef Novak, describes the situation in post-war interviews. We knew the gears were not right, could see it in how they looked after quenching. The color was wrong, but we said nothing. We were not German. Why should we care if German tanks broke down? Better that they break than kill people. If we did poor work, maybe the war would end faster. Novak's testimony reveals something important. The quality problems were not purely accidental. Some workers deliberately produced substandard components, sabotaged by negligence, allowing the process to drift, not reporting problems, not maintaining equipment. Small acts of resistance that accumulated into massive quality degradation. German supervisors knew something was wrong. Transmission failure rates from field units were reported, were documented, were impossible to ignore, but the production system could not respond, could not slow down, could not implement proper procedures. The pressure from above was relentless. More Tigers, more tanks, more production. Quality problems were acknowledged, then ignored. The priority was numbers. Numbers of Tigers completed, numbers delivered to combat units. What happened after delivery was not the factory's concern. This institutional failure is documented in German records. Reports from the Waffenamt, the German weapons procurement agency, describe the situation. Mention inadequate quality control. Mention skilled worker shortages. Mention production pressure. Recommend improved procedures. The recommendations are filed, not implemented. The system cannot change, cannot slow down, cannot fix the underlying problems. So the Tigers keep being built, keep being delivered, keep breaking down. By early 1945, Tiger transmission reliability is so poor that German tank units request different tanks, prefer Panthers, prefer Panzer IVs, anything but Tigers. The Tigers are too unreliable, break down too often, require too much maintenance, consume too many spare parts. The tank that was supposed to dominate the battlefield has become a liability, a maintenance nightmare, a machine that fails more often than it fights. Stevenson continues his analysis through the end of the war, examines Tigers captured in France, in Belgium, in Germany itself. The pattern never changes. Excessive hardness, inadequate tempering, brittle fracture. Every Tiger, every transmission, every gear. The problem is never fixed, cannot be fixed. The industrial system that created it cannot be reformed. By May 1945, Germany surrenders. Tiger production ends. The transmission problem becomes historical curiosity, subject for post-war analysis, lesson for future tank designers. Stevenson's work influences post-war British tank design significantly. When Britain develops new tanks in the late 1940s and 1950s, transmission reliability is a priority. Heat treatment procedures are specified precisely. Tempering is mandatory. Quality control is rigorous. The lessons from Tiger failures are applied. The result is transmissions that work, that survive combat stress, that do not shatter under shock loads. Stevenson retires from government service in 1955, takes a position teaching metallurgy at Imperial College London. His students know he worked on wartime projects, do not know specifics. Stevenson does not discuss it. The work was classified, the memories are complicated. He saved Allied lives by finding German weaknesses, but the weaknesses existed because German workers were exploited, forced to work under impossible conditions, producing equipment that killed their own soldiers. The morality is not simple. Stevenson did his job, analyzed the metal, wrote the reports. The strategic implications were someone else's responsibility. In 1976, a graduate student named Thomas Richardson researches tank reliability for his dissertation, contacts Stevenson, asks for an interview. Stevenson is 72 years old, retired but still lecturing occasionally. He agrees to meet. Richardson visits on a spring afternoon. They sit in Stevenson's office at Imperial College. Books on metallurgy everywhere, old journals, photographs of metal microstructures. Richardson asks about the Tiger transmission analysis. Stevenson describes it. The excessive hardness, the inadequate tempering, the brittle fracture, the realization that Germany was building tanks that could not survive their own power. Richardson asks the obvious question. Did you feel satisfaction, knowing that your work contributed to defeating the Tigers? Stevenson thinks carefully before answering. Satisfaction? No. The Tigers were defeated by their own inadequate manufacturing. I just documented it. Someone else would have found the same problem eventually. Probably a German metallurgist did find it, probably reported it, probably was ignored. The problem was not lack of knowledge, it was lack of ability to implement solutions. Germany could not slow production, could not fix the heat treatment, could not properly temper the gears, so the problem continued. I documented that, used it to understand enemy capabilities. But satisfaction? No. Just recognition of systematic failure. You are still watching. That means this content speaks to you, means you want more, means you understand that wars are won by people who understand how steel behaves under stress, who know what happens when you skip tempering, who recognize that hardness without toughness is brittleness. Subscribe now if you have not already. This channel exists to serve people like you, people who want engineering depth, who appreciate technical analysis, who understand that a Rockwell hardness reading of 62 HRC versus 58 HRC is the difference between a functioning transmission and a shattered gear. Subscribe, activate notifications, comment below telling us which German equipment you want analyzed next. Panther final drives, Me 262 turbine blades, King Tiger steering mechanism. Tell us. We listen. We create content based on what you want to learn. Subscribe now. Richardson includes Stevenson's analysis in his dissertation, published in 1978. The dissertation is titled Reliability as a Weapon, Mechanical Failures in German Armor, 1943-1945. The Tiger transmission receives an entire chapter, 28 pages, detailed technical analysis, metallurgical data, heat treatment specifications, failure statistics. The dissertation does not attract wide attention. Academic work rarely does, but tank designers read it. Metallurgists working in armor development read it. The information becomes part of institutional knowledge, part of how modern tanks are designed. Modern tank transmissions use gears with carefully controlled heat treatment. Case depth is specified precisely. Hardness is specified precisely. Tempering is mandatory and verified. Quality control includes metallographic examination. Sample gears are cut apart. Microstructure is examined. Hardness is measured at surface and core. Any deviation from specification results in rejection. The entire batch is scrapped if necessary. This level of quality control exists because of lessons learned from failures, learned from Tigers breaking down, learned from analyzing why. Stevenson's work is part of that learning process, part of the knowledge base that prevents modern tanks from repeating German mistakes. The German perspective on Tiger transmission failures emerged slowly after the war. Former tank crews wrote memoirs, described the frustration of mechanical breakdowns, described Tigers abandoned because they could not move. One commander, Hauptmann Otto Carius, who survived the war commanding Tigers on the Eastern Front, wrote extensively about transmission problems, described how his unit's operational readiness never exceeded 60%. How at least 4 of his 10 Tigers were always broken down, usually with transmission problems. Carius attributed this to combat stress, to difficult terrain, to inadequate maintenance support. Reading Stevenson's analysis decades later, he understood. The transmissions were doomed from manufacture, heat treated incorrectly, brittle gears waiting to fail. Nothing the crews could have done would prevent it. The tanks were mechanically unsound when delivered. Every mission was a gamble. Would the transmission survive? Would the gears hold? Carius wrote that knowing this was disturbing, knowing that he and his crews trusted their lives to machines that were fundamentally defective, that Germany sent them into battle in tanks that could not be relied upon, not because of enemy action, because of inadequate manufacturing. The feeling of betrayal was strong, not betrayed by enemies, betrayed by their own industrial system, by the decision to produce tanks faster rather than better, by the choice to ship Tigers with inadequate transmissions because meeting production quotas mattered more than reliability. Carius and other Tiger commanders felt they had been lied to, told the Tiger was invincible, found it was fragile, told German engineering was superior, found it was compromised. The psychological impact was significant, undermined confidence, created cynicism. Made soldiers question everything they were told. Modern analysis of Tiger tanks confirms Stevenson's findings completely. Museums preserve Tigers. Metallurgists have examined their transmissions, cut gears apart, measured hardness, examined microstructure. The results match Stevenson's 1943 analysis exactly. Excessive surface hardness, deep case, inadequate tempering, brittle microstructure. The problem was real, was systematic, was never fixed. The Tank Museum at Bovington, England has Tiger 131, the only running Tiger in the world, restored to operational condition. The museum maintains the transmission carefully, uses modern lubricants, limits operating hours, avoids heavy loads. Even so, the transmission requires constant attention, frequent inspection, careful monitoring. The museum's engineers understand they are operating a machine with inherent weaknesses. The gears are original, heat treated incorrectly, prone to failure. The tank runs because it is operated gently. In combat conditions with combat loads it would fail quickly. This validates everything Stevenson discovered. The Tiger transmission was inadequate for combat use, could not survive combat stress, failed regularly and predictably. The tank that looked invincible was mechanically vulnerable, crippled by its own drivetrain. This vulnerability was exploitable. Allied commanders who understood it could use tactics that stressed Tiger transmissions. Force the tanks to maneuver. Create situations requiring sharp turns and rapid acceleration. Each maneuver brought the transmission closer to failure. Some Tigers were defeated without firing a shot, defeated by their own gears shattering, defeated by metallurgy. Stevenson's analysis enabled this, made commanders aware, gave them confidence to maneuver aggressively against Tigers, knowing the Tigers might break down under stress. That psychological advantage mattered, made Allied tank crews less afraid, made them more willing to engage, knowing the invincible Tiger had feet of clay, had a transmission that could fail catastrophically, had gears that could shatter. Stevenson died in 1989 at age 85. His obituary in the Times mentioned his teaching career at Imperial College, mentioned his contributions to metallurgical science. One sentence mentioned wartime service. During the war, Professor Stevenson contributed to military equipment analysis. No details, no mention of Tigers, no mention of transmission gears, no mention of discovering that Germany's most feared tank had a fatal mechanical flaw. That information was in archives, in declassified reports, in dissertations few people read. Stevenson's family donated his papers to Imperial War Museum, including his wartime reports. The reports sit in archives now, available to researchers, rarely requested. The story of Tiger transmission failures is known to specialists, unknown to general audiences. The popular narrative about Tigers focuses on their firepower, their armor, their combat effectiveness when they worked, does not emphasize that they frequently did not work, that mechanical reliability was abysmal, that transmissions failed constantly, that the root cause was inadequate heat treatment. That cause was documented thoroughly by a British metallurgist in 1943. That documentation influenced tactics, influenced outcomes, influenced how the war was fought. This video brings that story out of archives, makes it accessible, explains the metallurgy, explains why the gears failed, explains how that failure was exploited, explains how understanding material science determined tactical decisions. This is the kind of content that matters. That reveals how wars are really won, not just through courage and firepower. Through understanding that a gear with 62 HRC surface hardness and inadequate tempering will fail under shock load. Through knowing that forcing a Tiger to turn sharply might shatter its transmission. Through exploiting knowledge, exploiting weakness, exploiting metallurgy. This video is ending, but your education continues. The next video in this series reveals another critical German equipment failure discovered by British engineers. Another story of technical analysis changing battle outcomes. Another deep dive into the engineering that decided who won and who lost. Subscribe now so you do not miss it. Click the red subscribe button below. Activate notifications by clicking the bell icon. Leave a comment telling us what you want to see next. Which German technology should we analyze? Panther engine cooling systems, Me-262 turbine blade failures, King Tiger fuel consumption? Tell us in the comments. We read every single one. We create content based on your requests. Subscribe now. Join a community of engineers, analysts, historians, and enthusiasts who understand that technical details matter, that metallurgy matters, that heat treatment procedures determine whether tanks work or fail, that wars are won by people who understand these details and exploit them. Wartech Archives, where engineering meets history, where we explain not just what happened, but why it happened, where we reveal the technical secrets that determined outcomes. Subscribe now. You will not find this depth anywhere else. No other channel analyzes heat treatment procedures. No other channel explains tempering temperatures. No other channel shows you microstructure photographs and explains what they mean. We do, because our audience demands it, because you deserve content that respects your intelligence, that provides real information, that teaches you something you did not know. Subscribe now. The story of Robert Stephenson and the Tiger transmission ends here, but the lessons continue in every tank designed since, in every transmission engineered to survive combat loads, in every quality control procedure that requires metallographic examination, in every specification that mandates proper tempering. The knowledge persists. The mistakes are not repeated. Modern tanks work because engineers learned from German failures, learned from Tigers breaking down, learned from gears shattering, learned from Stephenson's analysis. That learning saved lives, saves lives today. Every time a tank transmission survives combat because it was heat-treated correctly, Stephenson's work echoes. Every time a gear does not shatter because it was tempered properly, the lesson persists. That is legacy, not fame, not recognition, just knowledge applied, just problems solved. Just equipment that works because someone 70 years ago figured out why German equipment did not work. Stephenson did that, analyzed the steel, measured the hardness, examined the microstructure, wrote the reports, changed how the war was fought, never sought credit, just did the work. That is what matters. That is what this channel celebrates. The engineers, the metallurgists, the analysts, the people who win wars through understanding materials, through understanding that steel with untempered martensite will fracture, through applying that understanding. Subscribe now. More stories coming, more engineering, more metallurgy, more technical depth than you will find anywhere else. Wartech Archives. Subscribe now. You belong here.